Hello all. I hope this finds you safe and healthy at home. I hope you've enjoyed what has now been an extended winter break, even more so for you guys than for me. Look forward to seeing everybody next week, hopefully. Hopefully nothing changes. And while you may not be excited to be back, I do look forward to seeing everyone on Monday of next week. I do want to go ahead and jump into the semester. We don't have a lot of time to spare, and as you know, I mentioned last semester we're behind a few sections anyway. So I am going to leave you a quick little video to watch. This is going to be prep. I have a video posted from last year's class, but I missed like the first 3 or 4 minutes of the video that gets you started on the notes. So I'm going to do that right now. Once you are done with this video, so this probably shouldn't be much more than 3 or 4 minutes itself, jump over to the other video that is on Canvas and that I've shared. That will get you through the rest of the notes that I'd like you to do for today. All right. So see you guys on Monday. I'm going to pull up my document here. Hopefully you were able to get this off of Canvas and you can kind of follow along and take some notes if you're able to print. If not, just go ahead and do this on some blank pieces of paper. I will have hard copies for those who need them on Monday when we meet. But you'll see at the top here as we begin, it's called use substitution. And what use substitution is used for, it's still going to be integrating. Integrating is, if you remember correctly from what right before we left, is the idea of finding an antiderivative. One of the things I've kind of talked about many times is as long as we have a sum, such as this, quick little review here, we can go ahead and do the antiderivative of these term by term. So the antiderivative of x squared is this x squared over 2. The antiderivative of sine is a negative cosine, and if you remember, we always do that little plus c. What I've also said a few times is that we can't do products. At least we could not have done products before today. So that if I had x times sine of x, I can't just say that this is x squared times a negative cosine of x and then plus your c. If we were to test this and take the derivative of that, definitely doesn't bring us back to where we started from. So as we get into a little more complicated functions or complicated antiderivatives or integrals, then we need some different methods. And the first one that we're going to use is what's called use substitution. So in general, it's kind of considered the chain rule for integration, although it's not necessarily always for composite functions, but it is sort of the corollary to the chain rule back when we were doing derivatives. The big thing that we're going to be dealing with is use substitution can be used to integrate a function when integrand is a composite function. It can also be a product, it can also be a quotient, just basically more complicated functions. And what our ultimate goal is going to be is to take a complicated function and to create something that we know the antiderivative of. So it doesn't necessarily have to look like this all the time, but we just want to take a messy function, simplify it through some substitutions so that once I get this, I can use an old rule. In this case, it would be our power rule for antiderivatives, where we add 1 and then divide by whatever that new power is. If we can do that, then we've done our substitution correctly. So it's called use substitution. Our goal, so the first one I'm going to kind of step through, and this is partially done on the next video, and then you can click off this video, go to the second one that will have the rest of the problems that I want you to get through for today. Is this function right here. So I'm going to kind of jump to the function we want to find the antiderivative of. So we look at this. I'm asking you here to find the antiderivative of that function. So what I want you to recognize is there's a product here. So that's generally bad. 10x times that quantity, 5x squared minus a3. The other issue is this isn't just a 5x squared minus a3. It's raised to the power of 6. So unless we want to go ahead and multiply all of this out, 6 of these quantities, along with the product of that 10x, so that we can create this monster polynomial that we can then do the power rule. If we want to do that, we could, but obviously that would take forever, not a particularly efficient method. So use substitution is going to make this a little bit easier. So our steps, if we look at the top here, the first step is to pick the correct part of the function that you want to substitute for your u. So in this case, I said let u equal 5x squared minus a3. So I'm going to again do it over here so you can kind of follow how this is going to look in a second, but the work is also done on the paper. So I'm going to let u equal 5x squared minus a3. Well, if you understand what that means, I could rewrite this as remember, this is your u. This is what's inside of the parentheses. So I can now substitute u in here, and this is now what my function would look like. All right, so we have some u's. So here we have a u, but we also have these x terms. Like we've said a few times also, we don't want functions of multiple variables. It's not what we deal with in Calc 1. We want to get these in terms of the same variable. Since it's called u substitution, then that kind of implies we wanted them to all be u's. So what we're going to do next to try and get rid of these guys is come up to this function here. This is our function. Notice how we give this dx right here. The way we can always create a dx is by just taking our derivative with respect to x. If I told you to take the derivative of this function up here, then the derivative of u would be du over dx. Since it's a function of x, we're doing it in terms of x. And then when I take the derivative of the right-hand side, notice how I'm going to get 10x. Next thing, we always want to then solve for this little du right here. And the way I'm going to do that is by multiplying this dx term over. When I do that, what I am left with is that du is equivalent to 10x times dx. So if we revisit this function over here, notice how I have, I'm sorry, I copied this down wrong too, so you're yelling me at home from your computer screen, sorry. This should be 10x. I don't know where I got that 10x squared from. So 10x and then 5x squared minus a3. And then now if we kind of look and see what I've gotten, the derivative of this gives me 10x dx. So if we look at this 10x, and if we look at this dx, notice how the product of 10x and dx is equivalent to a du. So what that's going to allow me to do is I'm going to rewrite this u to the 6. That hasn't changed at all. But now these two terms here, the 10x and the dx, I can get rid of both of these. So I'm going to kind of just show I'm getting rid of both of those by, crossing them out, as long as I replace them with what those two things are equivalent to, which is your du. Once I've done this substitution, if I now tell you to look at this, what I have done is taken this original function here in terms of x, and through a substitution, I have created this function in terms of u. This one, pretty tricky to look at and know what the antiderivative is. This one here, though, really, really easy. This is our power rule. You're going to get u to the 7th over a7 plus your constant. Then since this started out in terms of u, we'd like to end up in terms of u. So instead of doing u to the 7th, remember what u is up here. U is at 5x squared minus a3. So I'm going to replace this u with the 5x squared minus a3, now to the 7th power, and now divided by a7, and then plus your constant. That is our final answer. We should be able to take the derivative of this and still end up with this original one. It gets a little harder to test all of these because they're a little messier, but I'll certainly do that with this one just to kind of show that this did in fact work. So if I told you now to take the derivative of this, again, I better start getting up with what I started with. So think about our rule here. This is really a 1/7, and I'm going to do the chain rule. So in the chain rule, I'm going to do 7 times this 1/7. Those would cancel. And what I would then be left with, we leave the inside alone. The new power becomes a 6. And then you remember in the chain rule, we've always got to do the derivative of the inside. And the derivative of 5x squared would be 10x. Plus, and then I got to do the derivative of that constant. Derivative of any constant is going to be a 0. So we just have a plus 0 there, which I will then erase. And then if we now look, isn't this the same exact thing that we started with up here? Confirms that that's the correct antiderivative. Our method worked. All right, from here, the rest of these are done. So if you go to the next video, I actually kind of pick up right in the middle of the problem that I just did. So you guys can then kind of jump to number 2 and then just I think you take you about halfway through these, and then we'll finish them off when we see each other next week. So again, hope everyone's well. Hope we're all safe. Hope we're all healthy. And I do look forward to seeing everybody next week. Take care.